which we are working on within AICS. So my talk will be organized roughly as follows. Let me start with who am I and what I'm doing here. And then I will talk a bit about the framework for the particle-based simulation, and I will also talk a bit about the frameworks for the grid-based simulations. Okay. The one thing I'm supposed to doing here is the team leader for the co-design team for the flagship 2020 project. Well, there's some official mission statement, but if I put what I'm supposed to do, or actually I have been doing for the last year in somewhat simpler words, it's roughly as follows. Today's microprocessors have become very complex, and as a result, to develop the applications which actually runs efficiently on today's microprocessor has become almost impossible. Well, if you don't agree, well, you can raise your hand or whatever. And what we are doing here is to make this impossible thing to somewhat less impossible. In the early phase of the microprocessor design, we try to predict what problems will occur, and if at all possible, try to fix that. So if the flagship, the post-K computer would turn out to be, well, almost impossible to use, that would be my failure. Okay. And the second thing I'm working here is this thing, the team leader for the particle simulator research team. And this is, well, again, the official word, but what we are actually doing is really simple. We basically we have developed the software system which we call the FDPS framework for the developing particle simulator. So for the main part of my talk, I will describe what is the motivation for this FDPS, and that is basically what we were actually what we don't want to do when we write the large-scale particle-based simulation code, and what should be done, and actually the design concept for the FDPS, and the current status and future plan. Well, what we want to do is pretty simple. We want to do the large-scale simulations. Okay, and this is an example of the simulation by Robin Canup in the Southwest Institute for the simulation of the giant impact. Giant impact is the collision between the proto-Earth and the Mars-type planet, which believed to be the trigger to form the place of the moon. And these are the sort of the state-of-the-art simulation, and this one actually still using only something like 1 billion particles, 1 million, not the 1 billion or 1 trillion. And well, the point here is that computers are, well, as people are here or know, computers have become fast enough to do much bigger simulations. But in many fields, well, of course, the people in here is the exception. You have the money and time and people to develop large-scale codes, but most of the scientists don't. So, and they are using the small machines and small code, and they don't really have the time to do the things we do here. People don't want to write Perl programs using MPI, and people don't want to modify the data structure or root structure or whatever of their legacy program, and they don't want to do the complicated optimization for example, to hide the interprocessor communication, or to use the SNMD execution unit, or even to use the things like the machine-specific language like CUDA, or, well, OpenShell is supposed to be open, but it's not quite. Effectively, it's a machine-specific language. Well, so what they do? Well, 30 or 40 years ago, there has been some hope that something like parallel compiler would solve the old problem, or the big shared memory machine, or something like the distributed shared memory machine would solve the problem, or the parallel language would solve the problem. But well, after 30 years, we all know that these things never happened and will never happen. Okay? And the reason is pretty simple. These things does exist, but their performance is pretty low compared to what you can do with handcrafted code. And the only thing that provides the best performance on the most inexpensive machine would actually survive in the field of HPC. So the question is what you or the rest of the people can or should do. What the people in this room is doing is either this one or this one. They accept the reality and write the MPI program and do the optimization, okay? And the limitation here is that if you are an ordinary person, the achieved performance will be low, and yet it will take more than infinite time to develop and debug your programs. And if you are not the specialty is not the computer science, your researcher life will finish, most likely finish before you actually finish the program. And of course, the other possibility is let someone else, postdoc or the graduate student, do the job. And of course, there will be the same limitation. If someone else is an ordinary person, the performance will be low, and it will take more than infinite time. So obviously, the neither approach is ideal. And the obvious thing, what we actually know is that we do need the non-ordinary people like these guys. These are the 2011 and 12 are golden winners. And quite a few of them actually in this room right now. So the problem with the non-ordinary people is quite simple. They are the quite limited resource, you know. Well, even in the world, I think there is much more than, I don't think right now more than a few tens of people can be really classified as the non-ordinary people, who can actually get the big reasonable use of the big machines. So there seems to be the need for a way to use the non-ordinary people for the many different problems, and that is what we are trying to do. The approach is to formulate an abstract description of the approach that those non-ordinary people do, and apply it to many different problems. And here, the many different actually means are relatively narrow, like just the particle-based simulations in general. And achieve this by means of so-called metaprogramming, and to be more specific, the particle-based simulation are parallel particle-based simulation basically includes things like the many fields and used in the many fields with the many different kinds of the particle interactions. But almost all of the calculation cost actually goes to the evaluation of the interaction between particles. And of course, for the case of the long-range forces like Coulomb force or gravitational interaction, you can use the 3-chord or fast Markov method or the particle eval methods. And these are actually used in all of the fields. So our solution is if we can develop a program which actually generates the highly optimized MPI program to do the basic things for the particle-based simulations, like the domain decomposition and particle migration, and the interaction calculation, and using the data available in other nodes, and for the given particle interaction, that can potentially be a solution. And what we are doing is basically write try to do the following things. And the user actually provides the particle data class and the function to calculate the particle interactions. And from those definitions, where actually for this one we use the C++ language to make it somewhat easier for us to generate the program. And our program actually generates the necessary library functions to do the complicated parallelization. And the users actually write their program using these library functions without the need to worry about the MPI communication and things like that. And the actual generation is actually done by C++ template functions. And the status of the code is that it is actually up and running. And the single user program can be compiled to the single core or OpenMP or MPI file programs. And the file efficiency is actually pretty high. I'll show the examples pretty soon. And as kind of version, we can also use the GPUs or other accelerators within this framework. And this framework is available on the GitHub here. For the domain of course, the most complicated part of the validation of the particle, the simulation is the domain decomposition. And we are using the same technique as we used for the codomain linear calculation by Shyama, and which is based on this kind of the domain of the recursive multiplication method. And this one actually works even well for up to 80,000 nodes, which is the maximum number we could try on the K computer. Well, this is a part of the sample code for the sample user code that the user actually needs to write. And this is the definition of the particle class with the mass and the position and the velocity and some of the necessary functions are to communicate with the FDPS part. And this is the function to actually do the particle interaction calculation. This one is written in the form of the function object, I believe. And of course, you can use the function pointer if you want to make the code somewhat simpler. And this is the standard way to do to evaluate the gravitational potential. And of course, this is not quite a way to get the maximum performance from the recent microprocessor with the SIMD instruction set. So you do need, at least for this part, in order to get the best performance, you need to write the code carefully so that the compiler can actually do the optimization, or just use the assembly language or intrinsic function to get the best performance. But for the example code, this works fine. And the actual things like the domain, the decomposition can be done in the single line of code to the functions after these particle class particle class and the interaction function is passed to FDPS. Okay. Well, so there are some remarks from the code, and you can actually define the multiple particle class if it is necessary, as in the case of the cosmological N-body, where the cosmological N-body plus hydro simulation in which you want to the matter and stars and gas particles. And the user-defined interaction function should be optimized. Well, this is what I told before. That should be optimized to the given architecture for the best performance. This program actually runs fine, fully parallel, with and without OpenMP or with and without MPI. And the total number of lines for the user code is pretty short, roughly 120 or so. And this is a example calculation of the giant impact estimation with this figure is generated with roughly 10 million particles, and up to 2.6 billion particles we have tried on K computer, and well, it turns out to be too easy to eat up all of the available computing resources, and we are trying to find some of the more machine resources in other machines right now. And this is the measured performance for the gravitational N-body simulation on the K computer and the Cray XT30 at the National Astronomical Observatory of Japan. Here is the number of nodes, and the black one is on Cray, and the white ones are on K computer. And here is the number of cores for the. And so, of course, the Hassel core sounds faster than the Venus core of the K computer, but of course the total machine set is much bigger, and we can get much higher total speed on the K computer. And this one is weak scale result with how many? Well, I'm not quite sure whether this number is right or not. And but this one is a weak scale result, and you can see that the work time per one time step is almost constant. And this one is the strong scale scaling result for the half a billion particles on K computer. And here is the number of MPI process, I believe, and this one is the work log time per one time step, and these white circles are measured values. So the strong scale result is fairly okay, very good for up to several thousand nodes. And after that, the time for the domain, the composition fit is shown in the red one here, and the communication cost would become visible. Okay. So to summarize on the FDPS part, it is up and running, and it's a framework for the developing parallel particle simulations, and it basically offers the library functions to do the complicated parallelization like the domain decomposition and particle exchange and interaction calculation. And it can be used to implement the pure N-body or SPH or any other particle simulation which can be written with the two-body interactions, and run efficiently on K or GM clusters or JG clusters. And well, it seems that a fair number of people actually start to use our FDPS software. You know, compared to writing the NPI program, even for the photon users, start going to move to C++ is easier. Well, so how about the state calculation? For the regular grid calculation, the parallelization itself is not so difficult. However, the performance is low and has been degrading for the last several decades, essentially because of the steady decrease of the memory, the relative memory bandwidth. So what we're trying to do is to well, work around this degrade in the memory bandwidth by means of the technique called the temporal blocking. The basic idea of the temporal blocking is that to read in a small localized region to the on-chip memory and update that region for the multiple time steps. So the simplest one is like this one. You start with the region somewhat bigger than these not by squares, rectangles, and you end up with that regime. And if you want to make if you want to make things more efficient, you can do this kind of form. But in this case, you can you need to finish this part. Well, what is going up? So the point is that you need to start from the right and go to left. And in this one, you can do the odd numbered region in parallel and then do the even vice versa. The even numbered region in parallel and then you can do the odd numbered region in parallel. But these are theoretically known, but the algorithm switch also parallelization in three-dimensional calculation and but not well known, and the theoretical limit for the bandwidth reduction is not well understood either. And we have worked on the parallel scheme for the three-dimension, and we obtained the theoretical limit for the bandwidth reduction. Well, I'm not going to go into the details here, but the problem here is again that ordinary people cannot write program which is so complicated like doing this. You need to do the calculation in the three-dimensional tilted plane in order to get the things done, and still you need to make use of the SRMD units and OpenMP and MPR and things like that. So the optimization and the parallelization will be more difficult. So here again, it is quite necessary that to take the similar approach like we did for the FDPS, and that's the program, generate programs. The idea has been there for many years ago. Example of is the Dexo system, which is provided by Hitachi on their Hitachi vector supercomputers. Unfortunately, Dexo is actually a pretty fine system, but it disappeared with vector machines. So in some sense, what we're doing is very much the de-embedding for it. And even so, we are currently working on this, and the language specification is ready, and the CAPI is ready, and the prototype version is actually working, and so that you can actually run the simple programs in our formula language and see it actually once done. This is an example of the code written in the formula language, and here is the definition of the finite different operators, and you can make it into the tuples and some macros, and the final form of the differential or finite difference scheme looks well. If you are working on this kind of stuff for the 6 months, you'd see that this is pretty close to the original form of the partial difference equation. But for the most of the normal people, the standard 7-point stencil may be much easier to understand. And basically, we can write this kind of the pretty basic stencil, which is compiled into the reasonably efficient and NPR parallels and hopefully temporal blocked code pretty soon. Okay, so to summarize, it has been very difficult to develop large-scale parallel programs and to achieve high efficiency. And we believe the framework can be a solution. And the point of the framework is to separate the physics and the numerical schemes and the parallelization and optimization. And the framework provides only the parallelization and the optimization part. And the application programmer can do the physics and the numerical schemes in the way which is independent of the parallelization. And for particle-based simulations, I believe is our approach will be used reasonably useful for many researchers, and for grid-based simulation, we are working on something similar. Thank you.